I'm going to do more descriptions, qualitative descriptions of 3 examples: water, carbon dioxide, and helium. And I've got some really cool videos to share with you all. So first of all, here is the H2O phase diagram. Notice it is a humongous pressure scale. This is a log scale, going from 1 Pascal to 1 terapascal. That's 1 times 10 to the 12th pascals. That's a lot of pressure. That's 10 megabar of pressure. Okay, and check it out on this phase diagram. Look, here is 1 bar. There is roughly atmospheric pressure. Okay, and this is what you're going to do in Igor 3. We're going to construct a phase diagram just like this. Okay. We notice here that if I scan across the atmospheric pressure, we get to the normal boiling point, right? 373.15 Kelvin, 100 degrees C. Okay, and if I keep scanning across that atmospheric pressure line, roughly, right, there is also now my normal freezing point. Okay, so consider, right, 1 bar is a 101.325 kilopascal, right, which is not quite atmospheric pressure, but very close. It definitely is standard pressure. Okay. So now let's see here. So 273.15 Kelvin, right there's our normal freezing point. Okay, and for water, what's pretty cool, we can see the triple point, 273.16 and 611.657 Pascal. So that's vacuum, right? So if 100 kilopascal is atmosphere, this is way down on the vacuum scale. Okay, so roughly 10 millibars, so that's like roughly 0.001 atm for the triple point of water. Okay, and now if we scan up, we can see, oh look, there's the critical point, and yes, that's PC, TC, and of course we don't see on this scale VC, those things that we were calculating using van der Waal and so forth. Okay. And what ends up happening at the critical point, and this phase diagram doesn't go much past the critical point, but I've got a really cool video to show you what happens at the critical point. The liquid and the vapor have the same density, okay? And there ends up being a really cool consequence as a result, okay? So the density of the liquid and the vapor is the same at the critical point, which is really cool. And now what you notice going on here for water, there is a whole complicated mess of different solid structures. We're normally used to seeing this IH, that's I-hexagonal. It's got a hexagonal lattice, okay? But it can also have a cubic lattice, that's what that IC means. It can have an orthorhombic lattice. And if you remember all of those things from George's class, then maybe that's somewhat familiar, okay? So I'm not going to go into all of these details, all these different crystal structures, but we will talk about those types of phase diagrams soon. So in other words, our normal phase equilibria, right, our solid to vapor, or our liquid to vapor, or our solid to vapor, that's what I'm going to start calling first order phase changes, okay? First order. And I'll just say that's like the normal stuff that we're used to, boiling, freezing, and so forth. All of these solid to solid phase transitions, so for example, like the phase transition from this IC solid phase to this XI solid phase, that's called a second order phase transition. And we'll see more examples of that in the coming lectures, okay? So I'm going to switch over to carbon dioxide, but little did you know how complicated water actually is, okay? So moving on. So now here's CO2. It's not quite as detailed of a diagram, but what you can see here, biggest noticeable difference, look, the boundary between the solid and the liquid has a positive slope. And I didn't talk about this here. It's really hard to see it on this scale. But as it turns out in water, the liquid and the solid boundary actually has a negative slope. That is the indication that the solid phase of water is less dense than the liquid phase, which is rare, right? Everything else has a positive slope right here between the solid and liquid phase, because everything else has a solid phase that is more dense than the liquid phase. There are other examples like water, but they're extremely rare. There are things like I'm going to get some of these wrong. I'll have to look these up and get back to you on that. But there are so few and rare examples like water. Everything else, nearly everything else, has a positive slope, indicating the solid phase is more dense than the liquid phase. Okay, so I'll point out here you can see the triple point of CO2 at 5 atmospheres and negative 56 degrees Celsius.